In this video, we are going to look at the 2013 AP Calculus FRQ problem number 3. Since this is one of the newer FRQs, you are not allowed to use a calculator on this problem. Pause the video and carefully read the problem. A few things to notice in this problem include the specified time interval from 0 to 6 minutes, that c of t is a differentiable function, and the units of c of t and t. Now we can look at part A. It asks us to approximate c prime of 3.5. Since the question asks us to approximate, we can take any of the available points left and right of 3.5 and calculate the slope by change in y over change in x. And since we know that the function is differentiable, we know that the slope at the point or its derivative exists. Because you can take any points left and right of 3.5, using c of 4 and c of 3 will make calculations simpler because the denominator is 1. The answer with units is 1.6 ounces per minute. If you are unclear about the resulting units, notice that c of t is in ounces and time is in minutes. Therefore, the change in ounces over minutes will result in units that are in ounces per minute. In part B, it asks if there is a time t when t is between 2 and 4 at which c prime of t equals 2. Immediately, you should think of the mean value theorem. To fulfill the mean value theorem, there are some conditions. A function needs to be continuous on the closed interval. We note that c of t is a continuous function because it is a differentiable function. But remember, all differentiable functions are continuous, but not all continuous functions are differentiable. C of t is differentiable on the time interval from 2 to 4 minutes because it is given in the problem. Now we need to calculate the slope on the time interval from 2 to 4 minutes. If this equals 2, then there is a time c at which c prime of t equals 2. In other words, the slope of the secant line from t equals 2 to t equals 4 would equal the slope of the tangent line on that interval at time c. Since the secant slope on the time interval from 2 to 4 minutes equals 2, then there is a time c where the tangent line at c also equals 2. In part C, the problem asks us to find the approximated value of 1/6 multiplied by the integral of c of t from 0 to 6 using a midpoint sum and 3 subintervals of equal length. The second part of the question asks us to determine the context of the integral in this problem. To use the midpoint sum and 3 subintervals of equal length to determine the approximate value of the integral of c of t from 0 to 6, we cannot make up points such as taking the midpoint from 0 to 2 using the midpoint formula. After sketching out the graph, we can see that the midpoints are every other point in between, so t equals 1, 3, and 5 are where we set the midpoints at. Now we can see that the width of each rectangle is 2. Since we know c of 1, c of 3, and c of 5, now we can calculate the midpoint area of these rectangles. The area that we just calculated is the approximate value of the integral of c of t from 0 to 6. Now we have to multiply this by 1/6 to complete the problem. To determine the meaning of this expression, you need to be able to recognize that this expression represents the mean value of an integral. Therefore, in this question, the mean value of the integral represents the average amount of coffee in ounces over the specified time interval from 0 to 6 minutes. Remember to be as specific as possible when writing out this answer, especially of the units of the integral and the time interval given by this problem. In part D, the question asks us to find the rate at which the amount of coffee in the cup is changing when t equals 5, given a function. This part is fairly easy. To find the rate at which something is changing, you would take the function's derivative. In this question, there is a simple chain rule application, and constants always become 0 when taking the derivative. After obtaining an expression for the rate of change, just plug in 5 and simplify. At time t equals 5, the rate at which the amount of coffee in the cup is changing by 0.64 over e squared ounces per minute. In this problem, each part of the question is fairly easy. Average rate of change, mid-value theorem, approximating area using rectangles, and taking the derivative with the chain rule. So while doing this problem, you should watch the time and relax. Some things to remember include, if a question asks you something on a time interval from A to B, always include the time interval in your answer or explanation. If you are approximating the area using midpoint and you are given a table, you cannot make up midpoints by calculating the actual midpoint between the 2 points. In this case, you use every other point in the table and its y value. Generally, if you are approximating the area using rectangles or trapezoids, always check if the widths are uniform. If not, you would need to add the areas separately and one by one. Lastly, remember your units by looking at the units given in the table or the problem. Here are some other resources and recommendations. For the mean value theorem, I would recommend just reviewing the needed conditions of a theorem and its conclusion. For more practice on Riemann sum using left and right endpoints, you can go to section 5.2 in the textbook and look through problems number 1 through 16. For midpoint and trapezoids, look at section 7.7 problems 7 through 18 while ignoring Simpson's rule. For review on the average value of a function or the mean value theorem for integrals and its meaning, look at section 6.5, pages 442 to 444. For part D, which involves the chain rule, you can go to section 3.4 and do problems 7 through 46 for problems on the chain rule.